Let's begin with the motivation for Bayesian classification. Bayesian classifiers are statistical models that predict class probabilities. They are grounded in Bayes' theorem, and a simple version, the naive Bayes classifier, performs competitively with decision trees and neural networks. One key benefit is their incremental learning capability. They update beliefs as new data arrives. Even when computationally difficult, Bayesian methods serve as a benchmark for optimal decision-making. Bayes' theorem lies at the heart of Bayesian classification. Suppose we have a hypothesis H that a data sample X belongs to a particular class. Bayes' theorem allows us to compute the posterior probability P, H X, from three components: the prior P, H, the likelihood P, X H, and the evidence P, X. Our goal is to compute how likely H is, given that we observed X. In prediction, we apply Bayes' theorem to find the class with the highest posterior probability. Formally, P, H X is proportional to the likelihood times the prior, divided by the evidence. Practically, we choose the class CI with the highest P, CI X. The challenge is estimating the many probabilities involved, which can be computationally expensive. When performing classification, we aim to find the class with the maximum posterior probability. Given a training set D and an input tuple X, we use Bayes' theorem to compute P, CI X, for each class. Since the evidence P, X, is the same for all classes, we focus on maximizing P, X, CI, times P, CI, instead. To simplify computation, the naive Bayes classifier assumes conditional independence between attributes. That is, the value of one attribute does not depend on the others. For categorical data, we compute probabilities using frequency counts. For continuous attributes, we typically use the Gaussian distribution with estimated mean and standard deviation. Here's an example dataset. We have two classes, Bayes_computer equals yes and no. We'll classify a new tuple with the values, age less than or equal to 30, income equals medium, student equals yes, and credit rating equals fair. Using the naive Bayes model, we'll compute the probabilities of this tuple belonging to each class. Let's walk through the example. First, we compute the prior probabilities for each class. Then we calculate the likelihoods of each attribute value given the class. Multiplying all these together gives P, X, CI. Finally, we multiply by the prior to get P, X, CI, times P, CI. The class with the higher value is our prediction, in this case, yes. A common issue with naive Bayes is the zero probability problem. If a class conditional probability is zero, the entire probability product becomes zero. To avoid this, we apply Laplacian correction, adding 1 to each count. This ensures that no probability is ever zero, keeping the model robust. Naive Bayes classifiers are easy to implement and work surprisingly well. However, they assume independence among attributes, an assumption that rarely holds in real life. For example, in medical data, patient attributes and symptoms are often interdependent. In such cases, more advanced models like Bayesian belief networks are preferred. Another approach to classification is using IFN rules. These rules are intuitive and easy to understand. Each rule has a condition, the antecedent, and a conclusion, the consequent. We evaluate rules based on coverage and accuracy. When multiple rules are triggered, we use strategies like size ordering, class-based ordering, or rule-based prioritization to resolve conflicts. Rules can also be extracted from decision trees. Each path from root to leaf forms a rule. For example, if age equals young and student equals yes, then Bayes_computer equals yes. These rules are mutually exclusive and exhaustive. They offer a simpler and more interpretable format than a full tree. Sequential covering is another technique for rule induction. Algorithms like FOIL, AQ, and Ripper generate rules one at a time. Each rule is designed to cover many positive examples of a target class while avoiding negatives. After a rule is created, the covered examples are removed. This process repeats until no good rules can be found. Here's the basic algorithm. While there are still positive examples left, we generate a rule and remove all the positive examples it covers. We repeat this until the stopping condition is met. This contrasts with decision trees, which generate rules all at once from the tree structure. Rule generation involves finding the best conditions, or predicates, to add to a rule. We use a metric called FOIL gain to evaluate each candidate. If the gain is above a threshold, we add the condition. Otherwise, we stop. This greedy approach builds rules incrementally with an emphasis on both coverage and accuracy. To learn one rule, we start with the most general rule and add conditions one by one, choosing the condition that most improves the rule's quality. We evaluate rules using FOIL gain, which rewards rules that cover many positives and few negatives. Rule pruning can be applied to simplify the rule without sacrificing accuracy.